All right, so today is Thursday, the 2nd of April, and this is Hydrogeology GEO 420 lecture. I'm recording this lecture. I will get videos posted on Moodle. It's been a bit of a struggle with getting all the videos uploaded onto Moodle. Well, actually uploaded onto YouTube, because I have 5 people in my house Zooming and video conferencing and trying to use the internet. And when I try to upload them, it just takes a ton of bandwidth. So I'm doing it at night, but I'm a little behind. I'll hopefully get all our lectures up by the end of tonight. So at any rate, they are being posted. You can download them. It's just subject to a bit of delay. Okay, so I think I'll start off. I'm going to lecture a bit about fracture flow, maybe get into a bit of freshwater, saltwater interactions today. But I want to leave some time for questions on homework. Yeah, go ahead.
Question on the homework side. I don't see a spot on Moodle to upload it to.
Okay. Why don't I just do that right now?
Okie doke, thanks.
I'm going to it's in week 11, homework 3. Okay, so what I want you guys to turn in, should be a homework 3 turn in site now under week 11. Please turn in a single PDF. All right, so if you have to take pictures, there's plenty of utilities out there to turn JPEGs into PDFs, and plenty of utilities to stitch all those PDFs into one file. All right, you guys are the digital generation. You should be able to figure out how to do that. It's not that hard. There's nothing that requires any money or any real hardcore computer savvy. So one PDF file, turn it in. I believe, let me make sure I can look at this here.
So you don't want to look at our Excel workbook at all? You just
Well,
want
let me, hold on, I just wanted to look at this. You should be able to turn in your Excel submission types, file submissions. Yeah, your maximum number of uploaded files is 20. All right, so I want one PDF and one Excel file.
Okie dokie.
Or whatever you used. If you used R or Python, whatever, just turn in your digital or your method of calculation for the curves. And you can submit them both easily. Yeah, if the only potential problem I see here, I've allowed you a maximum of 500 megabytes of storage. If you take if each picture of your homework is a huge file, I don't even think it's possible, but you might bump into 500 megabytes. I'd be shocked. If that's the problem, then in fact, I'm pretty sure if you turn it into a PDF, there's no way it's going to be 500 megabytes. So I don't think there'll be any problems. You can upload both files easily. Any other homework questions before we get started? Okay. All right. So
I have one real quick, Peyton.
yeah.
If we coded our equations, do you want just the raw code?
Yeah, I don't need anything other than just your script.
Okay.
Or whatever you used.
Okay.
Okay. Any other questions? All right. So I'm going to share my screen here. And we're going to start talking about fractures and fracture flow. All right, so let's start off by saying that fracture flow is one of the most complicated and hardest problems facing hydrogeologists. And the reason is that the hydraulic conductivity varies massively between the fracture and the adjacent rock, and that these fractures are sort of randomly oriented, and it's very hard to know where they are, how many fractures we have, and what sort of connections they have. So this will be, and always has been, one of the biggest and hardest problems for hydrogeologists working with fracture flow. And today what we're going to do is just talk about some of the basics of fracture flow and how do we sort of try and deal with some of the complexities. So the basic problem is that when we look at a fractured media, so let's draw a square of fractured media here. All right, so here we've got some box of fractured media, and what we'll have, let's say we go up and somehow get to look inside Mount Sentinel. We'll get these sets of fractures, and in a perfect world, they're sort of parallel-ish. And some of them will intersect. Get eraser here. Okay, so let's define some terms here. So I'm going to say I've got crystalline or any kind of, actually fractures occur in all different kinds of lithified rock. But so these blocks of intact rock, they get called matrix. And these can basically be any kind of hard rock, all right? And then in between the matrix, we have our fractures. All right. If we have so all of the fractures, or this, so let's say we're below the water table and all of our fractures here are full of water, just to start. Let's talk about some other terms. So this group of fractures we call a fracture network. And fracture networks, we characterize them by a few different measurements. So one of them we'll talk about is the sort of fracture density. That's how many fractures we have per unit area. So we're going to define a lot of these terms more rigorously, but just so we can get a conceptual idea, we have a fracture density. Which is basically some measure of how many fractures we have in our media. This is actually not as straightforward as you might think to characterize, but it's essentially how many measure of fractures per unit area.
Sorry, is it per unit area or volume?
Good question. Generally, we're going to start off right now assuming it's per unit area, because some assumptions we have to make is that these things move in and out of the board infinitely. And this is how we're going to measure it. So when we go and try and measure any kind of fracture density, all we get is like a face of a wall to look at, or the face of a borehole. So in general, what we're really interested in is per unit volume, but it's really hard to measure that. So most of the time we'll call fracture density per unit area, but I'm going to put volume here because that's really what we're after. All right. Other things that we might be interested in our fracture network are sort of the orientation, so the preferred orientation. So for a lot of geologic reasons, these things will often have a preferential orientation, and that's due to, say, the stress field at the time the rock was fractured. So we'll call that the fracture orientation. That's sort of the preferred direction. And there can be more than one of these. Okay, so fracture orientation. Another important, so another thing that you can't really see here because we've just considered a single cube, but these fractures never go on indefinitely. At some point, they tend to taper out, all right, and they'll close off. So we're not going to consider this in our class because that makes our life much harder. But there is, some metric that we're also interested in is what is the length the average length the fracture stays open for. So fracture length is another thing that we're interested in characterizing. All right. So we will talk about a few different things, but so as we sort of drill in towards one fracture, some things that we're going to talk about. Well, the width of the fracture is called the aperture. All right, so this is the fracture aperture. This fracture can either be open or it can have stuff inside it. So we talk about the fracture porosity. That is the porosity of the material inside the fracture. For us as a class, we're going to consider open fractures. And so the fracture porosity would be 1, all right? But you will hear this term in the literature, fracture porosity. It can mean, you got to sort of intuit what they're talking about. It can mean one of two things. One is the porosity of the material inside the fracture. And then we're going to talk about if we fracture density and fracture porosity often get mixed a bit. All right. If we are thinking about our entire assemblage of fractured rock, we might say, hey, this rock has this much fracture porosity in it. But really what we're talking about is fracture density then. Okay, so fracture porosity is the porosity of the fracture. So conversely, we'll often talk about matrix porosity. Which is the porosity of the matrix material. All right, so that is, so whenever we talk about fractured material, you'll often hear the terms dual continuum. So there's two units that we're talking about. One is the matrix, and it has its own porosity and its own conductivity. All right, and then we have fracture porosity and fracture conductivity. And these two make up our dual continuum. All right, so you'll often hear when people are discussing fractured systems, they'll talk about a dual continuum. There's two ways we talk about it. One is called a dual porosity. All right, and in a dual porosity system, we assume matrix has no permeability. So all the fluid flow is in the fractures, all right? There's always some hydraulic conductivity to the matrix, but it is often much, much lower than the fractures. So it just makes our life a lot easier to sometimes to assume that this has zero hydraulic conductivity, and we only consider flow in the fractures. However, if the rock itself has significant conductivity, we'll use the word or the classification of dual permeability. And this means that matrix has permeability and we need to consider it. Okay, aperture, porosity, matrix, some characteristics of the fracture network. All right, so this is all just vocabulary so that if and when you guys work in a fractured system, you can start to read some of these papers and you know, understand what some of this vocab means. Okay, so what we're going to do, so in real life, these fractures are very, very complicated. And we have fractures of a whole bunch of different lengths, all right, and different orientations. And another important thing that we often characterize in fracture networks is the number of intersections or fracture connectivity. You can imagine if I've got a fracture here that just is in my block and doesn't connect to anything. It's the exact same sort of idea as effective porosity. It's just a dead end fracture and it doesn't contribute to fluid flow. All right, so the number of intersections becomes very important, all right, in determining how well this fracture network's gonna transmit water. Okay, so when we work in real life, we deal with this really complicated system. It's got these sort of random sets of fractures. They generally have a preferential orientation, and we characterize them by sort of the density and the number of connections. What we're going to do in this class is, and what people mostly do when they work in fractured systems, is think about how to try and simplify the behavior and the characterization of this fracture network into a more like essentially parallel sets of fractures. So we're going to sort of zoom in and just think about, say, a plane that cuts through these fracture sets here, and think about parallel fracture sets. So let's open up a new page and talk about parallel fractures. So this is one way that we just try and simplify and deal with the situation is to just think about sets of fractures. So I'm going to try, let me change colors. I'm going to try and draw some straight lines here. See how I do. So we're going to say we have a regular set of fractures. All right. And it's important to remember that these fractures have some dimension in and out of the board here. Okay, so here are my matrix blocks. And okay, so I have these two parallel sets of fractures. And we're going to say they're regular. The fracture aperture, remember, is the width of this fracture. So we're going to call that B. So B is the fracture aperture.
Sorry, by regular, do you mean open?
I mean open, and the spacing is even. So they are distant. We have even fractures, and the distance between fractures is S, the fracture spacing. All right, and regular also means that they extend indefinitely in and out of the board. All right, they're evenly spaced, and they're extend infinitely in the vertical direction. So we basically just have this set of parallel planes in the rock. All right. We're going to consider, say, just some arbitrary height h here. All right, and then we'll talk a lot about some length here. L, all right, which includes two fractures and a matrix block in between. All right, so L is equal to S plus 2B. Okay, so let's talk about some important features of a fracture. So first of all, from a result in fluid mechanics, we get this, there's an equation for flow between parallel plates. And it says that the discharge, Q, is equal to rho water G B squared over 12 mu, where mu is the viscosity of water, times delta P, the change in pressure. All right, this is from fluid dynamic solution of the Navier-Stokes equation for a flow in between two parallel plates. So fluid dynamics. All right, so now let's think about this in terms of sort of a Darcy's law. We could think about this as the driving force, all right, like head, and this here is the hydraulic conductivity. All right, so we can write Darcy's for a fracture. Q is equal to K, A, delta H, delta L, right? And let's insert this for K. So we'll take this guy, put him in here, and then we'll think about what the area for a fracture is. All right. So Q is equal to rho water G B squared over 12 mu. All right. If I go up here to my drawing, what is the area, the area, let's say if we're interested in flow coming out of the board here, what is the area of this fracture? Across which flow is coming?
BH?
Yeah, B times H. It's the width times the height. All right. So Q, A, B times H. All right. Delta H, delta L. So let's make some. So this equation here gets called the cubic law because we can say this: Q is equal to rho water G B cubed. Over 12 mu delta H delta L. So this relationship that the discharge is a function of the aperture cubed, this gets called the cubic law. All right, and it basically says that our discharge out of a single fracture is a function of the cube of the aperture. So let's look at some other relationships. Well, first of all, the fracture conductivity is equal to rho water G B squared times 12 mu. All right. Do you guys remember what the equation for transmissivity was?
Wasn't it KH is equal to transmissivity?
K,
Or KB? KB.
K, so the transmissivity is equal to K times the thickness of the unit, which flow is occurring through the thickness of my aquifer. All right, so KB. So when we look at our fracture, the thickness which this is occurring or going through is really our fracture. All right, so the transmissivity of my fracture is this times this. So transmissivity of fracture is rho water G B squared over 12 mu times B. All right, so this equals rho water G B cubed over 12 mu. So this relationship, the cubic law, basically says that the transmissivity of my fracture, all right, is equal to the cube of the aperture, or a function of the cube of my aperture. I don't know why I put that there. So two important relationships: the single fracture hydraulic conductivity, rho water G B squared over 12 mu, the transmissivity of a single fracture, rho water G B cubed over 12 mu, and this gets called the cubic law. So a lot of times when you're reading a paper in fracture flow, they'll talk about the cubic law. All right, so here's an example. Here, this is a very famous paper in fracture flow, probably the most famous paper in fracture flow. I don't know if you remember, but the other author on the Freeze paper is Freeze and Witherspoon. Well, here's Paul Witherspoon again. It's a pretty good hydrogeologist, Cal. Here he's writing a paper on the validity of the cubic law. All right. So this cubic law is essentially this guy. All right. And you know, you can see right here. Here's the fracture flow equation, or the hydraulic conductivity of a single fracture.
What?
Okay.
I can't. Oh.
So if we have a parallel set of fractures, let's think about so if we have a parallel set of fractures, and I'm gonna, let's just put some more blocks in here. All right, so we've got our parallel set of fractures. All right, and again, this is H, this is B, this is L, This is S. All right. The total area of flow for a parallel set of fractures. So the area of fracture all right, it's going to be the area for each fracture times the number of fractures. All right, so we could say H times B times the number of fractures per unit length all right, so number of fractures that we have per unit distance here times the area of one fracture, right, would give me the total area of fractures in my fracture network. Now let's define this guy here, number of fractures per unit length, to be N. All right. Then my area of fractures is now H times B times N. And we'll call that A sub F, or the area of fractures.
So is that only if all the fractures are the same size though?
Yep. Parallel sets of uniform fractures. That's what we're going to turn the world into.
Okay.
Okay. So now my conductivity for this set of fractures or my flow, let's actually, let me hang on. So let's do it this way. Darcy's for fracture set. All right. Well, my conductivity is going to be the so K for my fracture set is going to be K times an individual fracture. All right. Times B times N. All right, so if we insert our definition for hydraulic conductivity, we get the hydraulic conductivity for my fracture set is equal to rho water G B cubed over 12 mu times N. All right. Let's think about how we could figure out N from the fracture spacing and the aperture. Well, if we have some unit length here, we're going to have a number of fractures per unit length. Well, let's just, I'm not going to get there yet. Okay. So a couple important observations. The hydraulic conductivity of a fracture network. So fracture network is a function of fracture aperture. And as Mark said, this would be some uniform fracture aperture or some average fracture aperture. All right. And the fracture spacing but the aperture is much more important. So spacing goes as a linear mapping, and the aperture goes as b cubed. So aperture is significantly more important than the spacing. Okay, so we can figure out the spacing N.
Sure. Is that kind of like the pore throat? How pore throat is
It's exactly like the
the
pore
most
throat.
important
Yep.
for permeability?
Yep. In the book, they say that the fracture spacing is equal to the cosine of theta F times or over S, the fracture spacing. Well, this is not fracture spacing. This is fracture number N. Where theta sub F is, let's say we've got a plane that we're interested in fluid flow across, and our fracture sets are intersecting this plane at an angle theta sub F. And S is this distance here that separates the fractures. Okay, so the bottom line is spacing, fracture spacing, S, and fracture aperture or average fracture aperture. Those are the two main characteristics that we're interested in if we're thinking about our fracture network as this set of parallel planes. All right. In general, what we tend to do, even though fractures aren't parallel planes in the real world, we try to think about and that the apertures aren't uniform. We try to characterize our fracture network in such a way that, like, we have an average fracture aperture that we use and an average fracture spacing that we use. And that those averages would be representative of the total or the average response of our fracture network. So this brings some super important points about trying to think about what we can and can't do in a fracture system. So we try to characterize, we try to get these average characteristics, say the average spacing. So network average is what we're after. And the same goes for aperture. So as Mark said, we need to think about that this is the network average. All right, so here is the rub. Because we have to move to these sort of network averages, it's really hard for us to be able to we can't predict the response of a single fracture or understand where and when we're going to have fluid flow in a single fracture. So in general, when we're working in fracture zones or fractured flow systems, we're trying to represent just a bulk and average response. And it's really hard to predict exactly what's going to happen and exactly where the fluid flow is, because we don't know exactly what each individual fracture looks like. So an example of this would be if you have a house in the mountains and you're trying to drill a water well, if you have a fractured block aquifer and you drill that well, you are only going to get water if you intersect a big fracture. And it's impossible for the hydrogeologist to tell you exactly where you're going to intersect a big fracture. But we do know that if you drill deep enough, eventually you're going to intersect a big fracture. So we should be able to know, like, how deep on average the well is going to have to be before we intersect a big fracture, given these sort of network average numbers, but we don't know exactly how deep it's going to be. All right, let's take a 5-minute break, and then we'll talk about one of the ways we deal with this averaging process is to think about the fracture network as an equivalent porous media. All right, so 5 minutes, and then we'll come back. Okay, so one of the ways that we can try and deal with the complexity of fractures is to scale way back out, and we introduced this idea of the equivalent porous matrix. All right, and the idea is that if we really scale out, all right, and so that we look at a very large scale of rock, our fractures are sort of crossing this rock at a high enough density that we can think about this thing a bit like grains and
Hey,
pore
Peyton,
throats. Yeah.
I'm not seeing your screen.
Oh, thanks. I forgot to do that the other on Wednesday, and my class didn't tell me for like 10 minutes. So
And
I was
nobody
just
said
lecturing
anything
and drawing
impressive.
away, and no one was seeing anything. All right. So the idea is that if we scale out far enough, if we zoom out far enough, our fracture network starts to look like pores. And our matrix blocks start to look like sediment grains. All right. And so probably the most common way people model or try to predict groundwater response in fractures is to make this equivalent porous media assumption. And what we try to do then is find equivalent parameters So we try to find equivalent porous media parameters that sort of represent average response of our fracture network. All right, so this is the way that we often try and deal with fracture flow. And again, I just want to reiterate that what that means is that we cannot say exactly what's going to happen in a fracture network. We can basically, at best, say this is what the average response is going to be. So prediction of exactly how water will respond at a given well in a fracture network is basically impossible. If our well intersects enough fractures, then we can do it well. But if our well would only intersect 1 or 2 fractures, it's a really bad situation for predictability. All right, so we can derive some of these equivalent properties. So let's do equivalent porosity first. And we can derive this for, let's say, parallel sets of fractures. So let's say I've got this parallel set of fractures. So here's my fracture matrix. And I've got a matrix porosity, NM. This fracture here, all right, has aperture of B. And the spacing between my fractures, okay, the spacing between my apertures, just like previously, this is S. And we're going to assume open fractures.
Those open fractures mean no matrix in them at all?
It means no, yeah, like if we were to zoom in on fractures in the real world, let's just zoom in on this guy. All right, so I got matrix on either side. All right, first of all, I'm gonna draw a real rock wall. All right, it's very rugged, right? So these points are called asperities. All right, so first of all, there's asperities. It's not smooth. And then secondly, we often have sand grains or bits of detritus in here. And so what ends up happening is that not all of the space here is available for fluid flow. You get dead zones in the asperities, you get sand grains in here. And so there is a fracture porosity that takes into account how much sand grains you have and how the asperities affect the difference between the real aperture and sort of an average aperture. But for the most part, and that's actually what this Fries and Witherspoon paper is all about, it's a pretty good assumption to say that the fracture porosity is basically open, all right? We can say that it's equal to 1. So if we assume open fractures, that means my fracture porosity is equal to 1. All right, in that case, my equivalent porous media, my equivalent porosity is equal to the matrix porosity plus B over S over 1 plus B over S. All right, so this gives me from a couple simple estimates or measurements of my fracture network. One is the average fracture aperture, and the other is the average fracture spacing. I get my and my matrix porosity. I can calculate an equivalent porosity. All right, so let's think about what this equivalent porosity looks like. So I want you guys to calculate. So one of the formations that I work in is the Garnet Stock up in Lubrecht. All right, and the Garnet Stock, the average fracture aperture we think is about 1 × 10⁻⁶ meters. All right. The average fracture spacing is about 1 meter. And the granite has a matrix porosity on the order of 0.01. All right, so calculate the equivalent porosity. What is my equivalent porosity in the Garnet Stock?
I got 0.01.
That's what I got as well.
Okay. So we got 0.01 plus 1 × 10⁻⁶ meters over 1 meter over 1 plus 1 × 10⁻⁶ meters over 1 meter. All right. This is, it's not equal to 0.01. It's equal to like 0.0100001 something. All right. But basically the equivalent porous medium porosity, the fractures are so small, all right, the aperture is so small that its N equivalent is basically equal to N matrix. Unless you have very large, fractures or your spacing is very small. So let's try it again in, so for the Garnet Range formation, this is a Precambrian belt it's a mudstone. All right, so Garnet Range. We have we've got B is 1 × 10⁻⁴ S is equal to 0.1 meters, and NM is equal to 0.1. So what do you get for N equivalent for the Garnet Range?
You scroll up a little bit.
What you need?
I just didn't copy down the equation.
There
Just
you go.
be about 1.
Yeah.
Rounding up, I get about 0.1009.
Okay. Zero 0.1009. Still pretty close to the matrix porosity. All right, so the bottom line is, in general, fracture porosity doesn't add a lot. This formation right here is really highly fractured. And even the garnet stock, that's moderately fractured. And still, it's not really changing the matrix porosity much. Okay, I got a question for you guys. How in the world did I get this measurement? How would you measure the fracture aperture?
Do you use seismic waves?
Potentially, but probably not. So the reason why is that this is 10 to the minus 6 meters. So that's roughly 0.01 of a gnat's ass. And seismic waves can't pick that up. So yeah, you could. People are trying, but it basically doesn't work. It's too small.
You just take a ruler out into the field?
Okay, so how many rulers do you know that measure at 10 to the minus 6 meters? That is a micrometer. So that there isn't many rulers that'll actually measure a micrometer.
Did you get it from first determining the conductivity of?
Aha! So KF, rho water, G, B squared over 12 mu. If I can measure this guy, all right, then I can get this guy. All right. So this is often how we try, and you got to get crazy to try and back this thing out. But generally, we do it in this manner. You can, if you've got core and you've managed to keep that rock intact, you can do things like CAT scan or various sort of really high resolution imaging. But it's really hard to get a chunk of rock out and not disturb the actual fracture aperture. So in general, we back it out through measurements of the hydraulic conductivity.
So you have to go around your elbow to get to your fourth point.
Well, not really, not really. This is easy. We can measure this in the field and we can get this guy. Now we have to isolate a fracture. So you have to isolate the fracture in order to measure this, and that gets pretty hard. Okay, so now let's talk about equivalent hydraulic conductivity of my fracture network. Okay. K equivalent is equal to the hydraulic conductivity of the porous media plus the area of the fracture over the area of the matrix times Kf, the hydraulic conductivity of a single fracture. 1 plus the area of a fracture times the area of a matrix. All right. If I have sets of parallel fractures, let's consider one unit, which is a matrix block and a fracture, right? And there's a plane of symmetry right here. So this is a symmetric unit. So the area of the fracture is B times whatever is in and out of the board. So let's call that L. So my area of the fracture is B times L. And my area of the matrix is S times L. All right. So we can make this area here if we have parallel fractures. We get okay. So matrix hydraulic conductivity for the garnet stock is 1 times 10 to the minus 8 meters per second. All right, if you don't remember or you lost your calibration, this is really low. All right, calculate the equivalent hydraulic conductivity for me. And as a reminder, B is equal to 1 times 10 to the minus 6 meters. S is equal to 1 meter. So in fact, this question's a little harder. So here's what I'm going to do. I'm going to break you guys out into groups. All right. And then I'm going to randomly assign one of the groups to talk about how they calculated it. So I'm going to send you into breakout rooms.
We'll need a mu value to calculate this, right?
Yeah, sure. All right, here you go. You're going into breakout rooms. Okay, welcome back. Looks like I forcibly ejected people. Most of you didn't join on by your own will. But okay, so here's what we're gonna do. I did a random number generator, and the number that came out was room 1. Right, so that was Holly, Jacob, Taylor, and June. Okay, so you guys, I'm going to share my screen. You're going to tell me what I need to write and what you guys did to solve for K equivalent. So what'd you guys do?
So we started by solving for K sub F. So we use the equation.
And what'd you use to do that?
The equation for a single fracture. So K sub F equals density of water times gravity times B squared over 12 mu.
Okay.
And we just looked up values for the density, or not for the density, but for viscosity. We use viscosity at 20 degrees Celsius, which is about 1.
1?
Yeah, 1.
1 what?
Pascal.
1 Pascal. Okay.
You don't like that value?
Well, Pascal's a weird unit.
I think it's 1 millimeter by something.
What's
too.
that?
It can also be 1 millimeter
Squared per second.
squared per second.
So usually viscosity is in Pascal seconds,
Mm-hmm.
not Pascals.
Well, I meant Pascal seconds. Sorry.
You meant Pascal seconds. One
Yeah, but I didn't
Pascal
say it.
second, that
I was
seems
thinking it, though.
pretty big. But usually it's on the order of like 1 times 10 to the minus 3 Pascal seconds. But all right, let's use what you got. Okay, so you're going to be off by, a couple orders of magnitude. It's all right. So density of water, what'd you use?
1,000 kilograms per cubic meter. Then times 9.8 newtons, or yeah.
Okay. And
then times R K sub M, or K sub, sorry.
Yeah.
Where am I looking here?
hold on, we're still here. What'd you use for B?
Oh yeah, B, sorry. 1 times 10 to the negative 6 meters squared.
Over 12.
Yeah, times our wrong viscosity.
So you have one something. We'll put Pascal seconds here. All right, what'd you get?
So our K sub F value was 8.167 times 10 to the negative 4.
Okay.
And then we plug that into our K sub equivalent equation. So K sub M plus B over S times K sub F over 1 plus B over S.
Okay.
So we plugged in values. So 1 times 10 to the negative 8 meters per second.
Let's
Plus
see.
1 times
I wrote this
10
equation
to the
down
negative
wrong.
6.
So this is, hang on. KM, KF. All right, 1 times 10 to the minus 8 meters per second plus
1 times 10 to the negative 6 over 1 times 8.167 times 10 to the negative 4th meters per second over 1 plus 1 times 10 to the negative 6 over 1. That gave us our K equivalent of 1.08 times 10 to the negative 8th meters per second.
So you basically got 1 times 10 to the minus 8 meters per second.
Yeah. Mm-hmm.
All right, what did other people get? Is that what other people got? 1 times 10 to the minus 8?
I got to the negative 6.
And so how
to the negative 8.
You got 10 to the minus 8
Not to the
too?
negative 8 as well. Yeah.
Yeah, we weren't sure which to use for B, the one that was to the -4th or to the -6th. So we did half and half.
Ah, right.
Yeah, that's what happened.
Okay, so most people are getting some between 1 times 10 to the minus 8 and something is wrong here. I can tell you that. It's
We used a
probably
much smaller mu as well.
You use the smaller mu. What did you get for your fracture permeability?
I used the smaller B, so mine was 5.669 times 10 to the -7.
Times 10 to the -7. Using the smaller B.
Yeah.
Interesting. All right, I'm gonna say I think that something is off. I got to figure out what it is. It might be my equation that I gave you, because the K equivalent should not be equal to the matrix permeability. So I'll come back and revisit this on Tuesday. All right, so we're at our end of our time for today. Let's revisit K equivalent for fractures on Tuesday. And we'll do a little bit of freshwater, saltwater interactions. All right, so we got homework due today, and then test 1 week from today. So Tuesday, we'll talk more about the test for sure, and what'll be on it, and how I'm going to deliver it, which I'm still figuring out. But most likely, it'll just be open book test. They have, and then the trick will be figuring out how to turn it in. So we're going to do the same thing. We're going to figure out how to have you guys scan it and turn it in as a single PDF. So that's the bottom line. All right. I'm happy to answer any questions, but our time is done. So if you need to leave, no worries.
You have office hours?
Yeah, I'm going to have office hours now.
Are you just going to stay and do it in this window?
I can, if people want to do it that way, that's fine.
Yeah, that'd be great.
That'd be great.
Okay. All right, so if you got questions you want to ask at office hours, go ahead.
So on the last question, when solving for the angles of refraction,
Yep.
is there a required angle to use as our first estimate? So our alpha 1, is there a certain angle based off the flow path that we should be using? Or is it just kind of choose one, estimate the angle, and then solve for alpha 2?
Yeah, so let me open up a new page. Homework questions. Okay, so basically you've got, some boundary, and you've got some flow paths coming in, and then they're going to do something. And your question is, what are they? You're given this right here. And so what you need to do is estimate this angle, right? So the best way to do this is with good old fashioned protractor. There are online or there are computer protractors that you, like an app that you can get, and you can lay it on there. But basically what a protractor will do is you lay this thing on here. Oh, I should redraw this.
I guess I mean, I understand how to estimate the angle. My question, I guess, more so is which angle do you use as your first alpha?
Well, basically you don't know this alpha. So let's say this is K1, this is K2. You're trying to solve for alpha 2. That's your question. This is alpha 1. And you got this equation. Let's see if I can remember it.
K1 over K2 equals tan alpha 1 over tan alpha 2.
All right, so what you're going to do, you're going to, this, you're going to estimate this, this.
Yeah.
So what you're going to solve for is this guy.
Mm-hmm.
And then once you have this guy, you can draw these flow paths.
Yeah. Well,
right?
yeah.
So I don't know, you got to figure out what this angle is, and then you can figure out what this angle is going to be.
And you can then draw your equipotential lines because that's still a square. So it has to be squares.
They don't have to be squares, but they have to be perpendicular.
Okay.
Right? They got to intersect these lines perpendicular. So the main thing here is that you got to maintain this right angle. Does that answer your question, Jacob?
Yeah. So I understood how to solve for your second angle. I guess my question was, when choosing which angle to use for your alpha 1, when estimating which angle based off your flow paths and how they interact with that boundary, what angle to use there. Because like there's a few different places you could choose to be your alpha 1.
Well, it's got to be alpha. This alpha should be the same. Alpha A is defined by this angle. It's the angle of the flow path with the normal of this plane, right? So this is alpha. And that alpha should be the same for all of these flow paths. You should always get the same alpha.
Okay.
So it's got to be this. It's got to be this angle, the angle of the normal and the flow path. And then you'll get this guy, alpha 2, which is the angle of the normal and the flow path.
Where's that normal coming from?
A normal is just the line perpendicular to the plane. So this is, let me erase this, clean it up. All right, you've got a plane, okay? You've been given flow paths that are coming in like this. And the question is, what happens to them afterwards? All right, so a normal is the line perpendicular to the plane at the point where the flow path crosses it. So the angle alpha is this angle here. And then you'll have some flow path after that. This is alpha 2. That is the angle with the normal for the new flow path. And this normal is basically the line that crosses the boundary, perpendicular to the boundary where the flow path is crossing the boundary. These have to come in and they got to cross the parallel here, and then they have to be perpendicular to our flow paths.
Thanks. Have a good day.
All right. Okay, other questions?
That red dotted line, that's perpendicular to the black line, which is like the line between the different conductivities, right?
Yep. This is called the normal, and it's perpendicular to the black line. And this is our contact.
Okay, thank you.
I have questions on problem 3.
Uh-huh.
So I've been using the equation to get Q using T, so it's K times B. I've been talking to people and they're not using the same equation, so
Okay, what is homework 3, or what is problem 3?
find total leakage per unit width of the dam. And you have a K of 65 feet per day.
Yeah, so first of all, so this is the dam equation, or the dam problem. So we've got our dam. And it was sitting on some surface here. It's got water on one side and water on another. All right, and had some depth. So first of all, so yeah, one of your first thing was to draw flow net, right? And then you need to calculate the flow under the dam.
Yep.
So what equation did you use?
I use Q equals NF over ND times transmissivity times the change ahead.
So let's think about what
Sir?
Yep.
You can't use transmissivity at this time because you don't have a B value.
Yeah,
Isn't
We
that
talked about this today.
Well, let's
If you use yesterday, we started off with the equation Q is equal to Ka dH/dL.
let's think about, so that transmissivity equation that came out of the book, and let's think about why they use transmissivity and why it doesn't really apply in this problem. So first of all, let's think about a flow net, right? So we've got two flow lines. And we've got these. All right, now there's some dimension. So we're going to think about flow through a single flow tube. All right, and there's some dimension in and out of the board here. Let me. Okay. There's some dimension in and out of the board.
Thanks, Peyton. I'm gonna head out.
Okay. Now, in the dam problem, this dimension, we're looking in cross section here, right? This is land surface and we're looking in cross section. So here we might call this W. In the book, they're doing this as if you're looking down on it, down on the problem. All right, so it could be B. It actually doesn't matter, but there's some dimension in and out of the board that's either looking vertically down or it's not, all right? So the discharge out of my tube, Q, we can write it from Darcy's, is K times A times delta H times delta L. All right, so this is delta H. Sorry. All right, so now let's think about what's A. Well, the distance between these two lines here, let's call delta psi, because
is that delta psi?
This guy is psi 1, this guy is psi 2. All right, these are my flow lines. So psi 1, psi 2. So this distance is delta psi. All right.
All right.
So we got delta psi, and then whatever this value is here, W or B, whatever you want to call it. I'm going to keep it W here. So it is delta psi times W. It's just the face area of this face here.
Yeah.
Right? Does that make sense? Okay. So now let's write Darcy's login. K times A delta psi times W
times W. Yep.
Times delta H over delta L. All right, now let's think about it. So this here is delta L. If this is a square, the definition of a square, because we made this flow net, this is a square. The definition of that square is that delta psi is equal to delta L. Do you agree with that? So in that case, these two cancel out. K times W times delta H over delta L.
No, you.
Oh
your
yeah,
delta
cross.
L goes away, sir.
Yeah. Okay, so this is the flow out of one stream tube. If I have a bunch of stream tubes, it is NS times K times W times delta H. All right. Now the question is, how do we calculate delta H, the head drop between each contour? All right, so there's two things you got to think about. Delta L is the distance between contours. Delta H is the head drop or the contour interval. So this is the contour interval. Well, if I know the head here, H1, and I know the head here, H2, and I have 1, 2, 3 head drops, then delta H is equal to my total head drop, delta big H, over the number of contour intervals.
That's where it comes from.
So now I have Q is equal to NS over NH K times W times delta H. All right, so now this is the most general equation. It says the discharge here is equal to NS times NH times K times whatever unit I want to think about in and out of the board, W, all right, times the total head drop. Now, if I'm looking down in plan view on my aquifer, so if I'm looking down, then Q is equal to NS NH K. My distance in and out of the board is B, the aquifer thickness, times delta H. And there we can put transmissivity in there. All right, so what the book is doing is saying, hey, if you're looking down and you have a flow net and you're looking vertically down, you can calculate the flow through there using transmissivity. And what they've done is they've put B in for W. That's what looking down does. It says I can put B in for W, and then I can use transmissivity. But here, what you're asked to do, I want you to calculate discharge per unit width in and out of the board. All right, so here I just move W over here.
Sir, because you didn't give us a width, that's why we can't, or transmissivity includes the thickness. That's why you can't use that equation, right?
Yeah, it doesn't. Transmissivity includes the aquifer thickness. It is a vertical measurement, so it doesn't make sense to have a horizontal transmissivity. So yeah, first of all, I ask you to calculate the discharge per unit width in and out of the board. So that would be per unit width of dam, how much flow is coming under the dam? Well, this equation will give me that.
I guess what I mean is transmissivity is K times B. But so that means that B is locked up on the right side of the equation, and we can't break it out.
No, again, you can use transmissivity if you're looking down on your problem and you're calculating the unit discharge per horizontal for a horizontal tube. But here we're looking sideways, we're looking in cross section. The main point here is that the area of your face here, it's not the total thickness of your aquifer, it's just some unit underneath the dam.
Okay.
We're just calculating it for some vertical column here. And W is this width.
Can we look at the last part of 3.2? It says, if the material under the dam is a fine loose sand, calculate the critical hydraulic gradient.
Yep.
And determine if it is exceeded at location X and will quick conditions occur. I am having a hard time remembering what this stuff was. I know it's in my notes for right before spring break, and I can't go back and look at a lecture.
Well, we defined the equation for the critical hydraulic gradient, I crit. And basically there's a simple equation for that. Let's see if I can. It was rho S. Oh. All right, so this is my critical hydraulic gradient. So you calculate what your critical hydraulic gradient is, and then you use your flow net to, so this will give you some value, whatever it is, X. All right, and then you compare X to your gradient, DH, DL, in your flow net at point X.
I'm confused how you do that at point X because there's like no change in head above that point X directly. Or is it just the whole hydraulic gradient through the whole aquifer?
No, you. Okay, so first of all, when I'm looking at a topo map, all right, let's say here's a topo map of Ranger Peak. If you don't know where Ranger Peak is, it's in the Bitterroots. All right, so these are contours of the elevation. All right, these are 10-meter contour, or these are, yeah, whatever. We'll call them 10-meter contours. All right, where is the cliff on this mountain?
It's on the northeast side.
Right? So here I'm getting 10 meters really steeply, right? Over a very short distance. Here I've got 10 meters over really long distances. So if I'm a normal person, I'm going to climb Ranger on this ridge. If I'm a crazy person, I'm going to climb Ranger up the cliff. All right? I can tell the gradient in elevation by the distance between contours. All right, so I can tell you what the gradient of the elevation is at this point by looking at the distance between contours at that point. All right, I can tell you what the gradient in elevation is on the ridge by looking at the distance between contours at that point. So you've got a flow net, you've got head contours. You can tell me what the gradient in the head is by looking at the difference in the head contours. So this is DH and DL. So the head contour gives me head, and the length between the contours gives me DL. So you get it from your flow net. Your flow net allows you to calculate the head contour or the gradient in head at any point here. So here I've got a really long distance between head contours. All right, I have a low head gradient. Here I've got a much shorter distance between head contours. I've got a much tighter head gradient. So I can look right at my point and I can look at what the distance along my flow path. All right, I can see what I can measure DL, and I know what DH is from my head contours.
How do you measure DL? You just take a ruler on your contour lines?
Uh-huh.
Yes?
Yeah.
And the same thing with DH?
No. How do I measure DH?
So the head drop, so here it says 10 feet from below 6.
Well, I don't, what?
No, isn't DH the total head drop divided by the number of contours?
That gives me the contour interval. So you know what the value of head is at each one of these contour intervals. Each one of these, let's say the head here is, I don't care what it is, 10, here it's 3. I've got 1, 2, 3, 4, 5, 6 drops. I'm going to put another one in so that it's 7. So 10, 3, 1, 2, 3, 4, 5, 6, 7. So my total head drop is 7 meters. My number of contours is 7. So each contour here is 1 meter. So this guy is 9 meters. This guy is 8 meters, 7 meters, 6 meters, 5 meters, 4 meters, 3 meters, right? Each one of these contour intervals is 1 meter. So all I got to do is measure the distance between these two, right? And then I know what DH is. It's 1 meter.
Is that where the 50 comes in, sir? At the bottom of the picture, you have a bar of 50 feet.
Yeah, that's your scale.
Yeah, that's the scale.
That's the scale.
That's what we would use to measure the distance between our flow lines, or
that's what you use to get the scale.
7 meter.
And so then if we can calculate our head gradient in our diagram.
Yep.
It is.
I can calculate the head gradient anywhere on here. I've got a flow net. I've got values of the head contours. And so it's easy for me to get DH. All right, that's just different head the value of my head contour. And I got DL, that's just the distance between the two head contours.
So then our critical head gradient is just the average head gradient over the.
No, your critical head gradient, you get your critical head gradient from this equation. This is what this is what you would need to have quick conditions. And then you can calculate your head gradient at any point. Let's say I wanted it right here.
Oh, and you compare.
Well, I would calculate DH. I know what DH is. I would look at DL here. And I would say, okay, this is 1 meter over whatever length this is. 10 meters. Is that, if DL is 10 meters, this is 1 meter. Is 1 meter over 10 meters greater or less than my critical gradient?
Okay.
And I could make you do that anywhere. I could say, oh, well, what about here? What about here? What about here?
Could we also go over problem number 5? That seems to be the trickiest one on the problem set.
Which one's problem number 5?
Problem number 5 is you're plotting water retention curves using the green ant formula for the last part of number 5.
Yeah.
So calculate an infiltration rate.
So what do you want to know?
So plotting the water retention curves, I'm not sure like how to get water content, because that's on the y-axis for water retention curves, right? Volumetric water content.
Well, I mean, these are basically just all you do is this is just an application of, let's say, Brooks Corey here. SE is equal to lambda B or psi B over psi to the lambda or 1. Depends on if psi is less than psi B or psi greater than equal to psi B. And then I know SE is equal to theta minus theta sub r over n minus theta sub r. All right, so if I was doing this, I'd make a column of theta sub w. I'd make a vector where it ranged between psi sub r to n. A bunch of values. All right, from those values, I would calculate SE. So I would get a column of SE, and it would go basically from 0 to 1. All right. Or actually, here's what I would do. You are given this relation. You can either solve these, reverse these, and do it the way I was doing, or you can pick a range of size from something really negative to 0. All right, that's the water table. For each one of these size, I then calculate SE. So you're going to get a vector of SE values. So SE from with a psi of negative 100 to an SE when psi is equal to 0. All right?
And what is SE again? I forgot.
It's this.
Yeah, but what does it stand for?
It's effective saturation.
Okay.
All it is your water content. It's your volumetric water content. It's just normalized by the full range that you would expect to see. So fully saturated to residual saturation. So when this thing is equal, when you're fully saturated, theta sub W is equal to N, and SE will be 1. Your effective saturation is 1. When you're at residual saturation, theta will be equal to theta sub R, and SE will be equal to 0. So this just normalizes volumetric water content to vary between 0 and 1, between full saturation and residual saturation. That's all it does. All right, so then I would plot from this equation, I would get theta sub W for psi equals a negative 100 and psi equals to 0. This range of values. And then I would plot theta sub W versus psi. I would use this vector of numbers and this vector of numbers, and I'd make a plot. Or sorry, psi, I want you to do psi versus theta sub W. So you choose a range of these. Using this equation here, you calculate SEs. Using this equation here, you calculate theta sub W's, and then you make a plot of these two.
Which equation do we calculate theta sub W with? Is it the SC equals theta over theta R?
Yeah.
Over N minus theta
You just gotta solve for this guy.
Mm-hmm.
You're gonna have this. You want to solve for this, and that'll give you this.
And you're gonna have SE from when you were solving for it up here and just putting it.
That equation's going to give you SE.
Can you keep the Dropbox open until tomorrow?
What's that?
Could you keep the Moodle Dropbox open until tomorrow evening?
It'll be open.
Okay. Thank you.
And so then we plot these for part A and B, water retention And then to do the green amps function, do we have to like interpret our graphs to get the given values to put in?
No, for the green amped, the big thing you need is H sub F. That's the psi at the wedding front. And there's an equation in the book to give you H sub F. But it is basically, it's a function of lambda. What is going on? Turn off. H sub F is a function of lambda and psi sub B. So you can figure out your, this is in the book. But for each, basically for each water type, you're going to have this, you're going to have this, and you can calculate H sub F. Once you know H sub F, you can figure everything else out for the green amped function.
In 5C, it gives you a standing water height of 5 centimeters on a
5C gives you what?
In 5C, it gives you a height of standing water on a soccer field. Is that your ponded water depth?
Yep.
Okay.
So H sub F, the equation for estimating it is this: 2 plus 3 lambda over 1 plus 3 lambda times psi B over 2. So you can calculate H sub F for each thing. You have H sub S, which was 5 centimeters. Everything else you get from the characteristic properties of each sediment.
And where did you say we get lambda again? Is lambda is a given value in that table? Is that where it is?
Yep.
Okay. And then theta S and which is saturated water content and initial water content. Will we get those out of the table as well?
Yep.
In the table, it says theta R. Is that like equivalent to initial water content?
Well, yeah, because I said you could assume that the soil was fully drained.
Could you try posting your lecture from Tuesday sometime during today?
It's probably not going to get up till tonight. It sucks all the bandwidth in my house to upload these videos. So it'll be later this evening when it gets up.
Okay.
I'm having trouble finding where saturated water content theta S would be in the table. It gives a value for theta R. It gives a value for porosity.
Mm.
Gives
What's
a value for,
what's the value for theta sub W when you're fully saturated?
51, right?
Remember, theta sub W, the definition of theta sub W is volume of water over the volume of REV. So if I'm fully saturated, that means all my pore space is full of water. What is the max value of theta sub W?
Porosity.
Yeah. The most
that makes
water
sense.
I can get in there is to fill all the pore space with water.
So then in our function, we can just replace theta sub S with N.
Yep.
Okay. In 6B, you're given a scenario where there's a tailings pond and contaminants are flowing towards some city wells. And the city wells are in like a gravel outwash plain with a pretty high hydraulic conductivity. And it says, do you think that the city well field would be impacted by the contaminated groundwater?
Yep.
Conductivity?
You broke up, so you need to.
Oh, sorry. Could you say yes, because the city wells would be contaminated because of the high hydraulic conductivity?
Well, you don't just get to say yes or no. You gotta make some calculations and decide and tell me whether or not they're going to be affected. So yeah, we don't just get to wave our hands.
Dang.
But it's an application. We've been talking about this earlier. It's an application of flow path refraction. So you gotta calculate from the incoming flow path and the hydraulic conductivities. So here's my incoming flow paths. You've been given, or you can measure these incident angles. Then you got to tell me, then you got to calculate and then draw the resulting angles as it moves into that high hydraulic conductivity material. And you got to tell me whether the flow path refraction would result in the wells being contaminated or not.
Oh, so it has to do with like the trajectory of the groundwater flow. If it's at the right angle, then it'll go to the wells, but if it's not, it won't. Okay.
Yep.
What's the formula for that instance of refraction stuff? Is there a general formula for that?
Yeah, it's right here.
Okay, cool. Thank you.
Okay, any other questions?
Yeah, I'm having a problem with number 3 that we were working on, part C. I just don't really understand what it's asking. And then I think I might be using the wrong equation because I'm getting weird numbers. But it says if the dam is 250 feet wide and the flow is 50 cubic feet per second, will the reservoir stay at full pool, or does the water balance suggest leakage will act to lower the water level? Is that, like, I'm just having a hard time visualizing what's happening, because if the water's coming in to the top, is that asking if it's like too much for what's coming out the other side?
Okay, so first of
Or
all,
not enough?
yeah. All right, so first of all, let's talk about, so you calculated from this equation, you calculated the discharge per unit width of the dam.
Yes.
So if I want to know the total discharge under the dam, it is equal to Q over W, this guy that you calculated,
Yeah.
times W, times the width of the dam. Right? So that'll give me the total discharge under the dam.
Okay. Okay.
All right? Now, the second question is a mass or a reservoir balance. So how do I know, how would I decide? So I have some amount of water coming in, Q in, that I gave you. It's coming into the top of my reservoir. How do I know whether this reservoir would be filling or draining?
If there's a head drop, because that's what I was trying to calculate.
Well, yeah, so I've got some discharge under the dam. I got some leakage under the dam. I got some coming in. I know
Okay,
that
so
my
if Q out is
reservoir,
greater than Q in.
what's that?
So if Q out is greater than Q in.
Yeah, so if Q, the change in storage in my reservoir is equal to what's coming in minus what's going out. All right. If what's going out is greater than what's coming in, then I know I'm going to drain my reservoir. All right. So the key is to calculate this leakage, compare it to what's coming in, and then you'll know whether you're going to be draining your reservoir or whether it will stay full.
Okay, that's much simpler than what I was trying to do. Thank you.
Can you scroll up real quick and just show that diagram for the contacts between the two hydraulic conductivities? Right there. Thanks.
Thanks for your help.
Yeah, you're welcome.
See ya.
Yeah, thanks for the help.
Thanks.
Cheers.
Have a good day, sir. Oh, yeah. Have a good day.
Bye.
Thanks, Peyton.
Is this just me and you right now?
I think so.
Okay. I just wanted to talk about the test next week.
Yep.
So is there a way to like give up me extended time on Moodle, or have you not figured that out yet?
Yeah, I'm going to have to figure that out. I'm not exactly sure how I do the timed thing. But yeah, you and Mark will get extended time.
Okay.
So But I don't even know how they're still trying to help us figure out how we do that, like a timed turn in. But regardless, like everybody's going to have to get a little more time because they got to figure out how to convert the file into a PDF and submit it. So
Yeah.
everybody will get a bit more time, but I'll let you and Mark have more.
Okay.
And it'll be the same as for your, previously. I can't remember what we did for you guys. Did you get double?
I got 3 times.
Yeah.
The usual allotted time. But
So yeah.
Yeah.
Well, I think what I need to do. Does DSS have? I would email DSS and just tell them we got an exam coming, and what they'll let me know what I agreed to for the time allotment. But basically, I'll honor that.
Okay. Do you want me to CC you on the email?
Yeah, sure.
Or does it matter?
I'm not. Yeah, I don't know how I'm gonna do it, but I actually don't know how to do it, but I'll figure it out.
All right. Sounds good.
It might be the kind of thing where everybody's just going to get more time, and that's just what it is.
Yeah.
But we'll see.
All right. Well, thank you for everything.
Yeah, you're welcome.
All right. See you next Tuesday.
See ya. Have a good day.
You too.